Remember the definition of a second-order homogeneous linear differential equation. It's written as the second derivative of y times a coefficient like a sub 2x plus a sub 1x times y prime plus a sub 0x y equal to 0. Assuming that a sub 2 is not 0, we can divide by a sub 2 and write this guy in standard form. The standard form can be written as the second derivative of y plus px y prime plus qx y equal to 0. Please note that px is equal to a sub 1x divided by a sub 2x, and qx in the same manner is a sub 0x divided by a sub 2x. Another definition was ordinary and singular points. A point like x sub 0 is said to be an ordinary point if both px and qx are analytic at x sub 0. What's the meaning of being analytic at x sub 0? It means that both of them have power series representation. If you have any types of polynomials, they are basically analytic at any point. Any point that is not ordinary point is called a singular point. Our goal is to find power series solution for a differential equation. So suppose you have the second derivative of y plus y equal to 0. We want to find a power series solution for this differential equation. Please note that here you have no px is equal to 0, which is analytic, and qx is equal to a constant function 1, which is also analytic. So let us begin. In finding the power series solution for the differential equation here, we use a general definition of power series. A power series around the point 0, which in this case is going to be the center given to us, is written as y equals to a sub 0 plus a sub 1x plus a sub 2x squared plus the rest of the terms, a sub n x to the n plus the rest of the terms, which in turn can be written as the summation of a sub n x to the n when n starts at 0 goes to infinity. So what's the first derivative of this power series? You take the derivative term by term. When you're taking the derivative of a sub 0, the derivative of this guy disappears. This derivative is 0. A sub 0 prime is 0. So if you take the derivative term by term, the derivative of a1x is a1, the derivative of a2x squared is 2a2x, and the derivative of general term an x to the n is an x to n minus 1. You continue the process, and in general, if you have an x to the n, the derivative is an x to n minus 1. But please note that since the very first term disappeared, you start in your power series at 1, not 0. With the same process, if you take the derivative of a sub 1, the derivative of a sub 1 is equal to 0. So if you take the second derivative, you get 2a2 plus the derivative of rest of the terms, and the derivative of general term is n minus 1, an x to power n minus 2 now, plus the rest of the derivatives, or in more general form, you get the summation of the derivative of n times n minus 1, an x to power n minus 2. And again, please pay attention here. Since your very first term disappeared, you're starting your power series at 2 now. Okay, we found the derivatives. Now we need to substitute them back into the differential equation here and try to simplify as much as we can so we can find the recursion. The second derivative of y, as you saw, is 2a sub 2 plus the rest of the terms, n minus 1, an x to power n minus 2, plus the rest of the terms. This guy in turns can be written in compact form as the summation of n minus 1, an x to power n minus 2. So again, this is just the second derivative of y as the power series summation plus y, which is a sub 0, plus a sub 1x plus a sub 2x squared plus the rest of the terms, an x to the n. We are just substituting a power series for y, or in compact form. This is the summation of an x to the n. And on the right-hand side, we set them equal to 0. Our goal is to find the recursion for a sub n. But at this point, in order to combine these two series, we have to shift the index of the summation by replacing our n by n plus 2. So our first power series becomes the power series starting at 0. Wherever you see n, you're going to replace that by n plus 2. So n becomes n plus 2, n minus 1 becomes n plus 1, an becomes an plus 2, and x to power n minus 2 becomes x to power n. You're going to copy down the second series as it is. And now that your series have the exact same starting point, the indices are the same, and your x has the same exponent n, you're allowed to combine these two power series. These are basically polynomials that you try to combine together. So you get the summation of n plus 2 times n plus 1, an plus 2 plus an. We just factored out x to the n, right? And you set it equal to 0. So far we saw that the summation of n plus 2, n plus 1, an plus 2 plus an times x to the n, and starting at 0 to infinity, is equal to 0. We're trying to find the recursive formula here. So you get the coefficient and you set the coefficient equal to 0. But what's the meaning of that? It means that n plus 2 times n plus 1 times an plus 2 is equal to negative an, or an plus 2 is nothing but negative an divided by n plus 2 times n plus 1. So let us begin, everybody. I'm going to plug in 0 into the recursive relation. So let n be equal to 0. I get a sub 2 to be negative a sub 0 divided by 2 times 1. Or I have negative a sub 0 divided by 2 factorial. Remember the definition of factorial. Then you have k factorial. This is k times k minus 1 times k minus 2 dot 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 2 times 1. So 2 factorial is 2 times 1. Now let us plug in 2. I'm working with even indices right now. So when n is equal to 2, a sub 4 becomes negative a sub 2 divided by 4 times 3. But pay attention here. You already calculated a sub 2. A sub 2 is a sub 0 divided by 2 factorial. It has a negative sign in front of it. So a sub 4 becomes a sub 0 divided by 4 times 3 times 2 factorial, or 4 factorial. In the next step, I'm going to plug in 4 for n to find a sub 6. So when n is equal to 4, a sub 6 becomes negative a sub 4 divided by 6 times 5. But again, pay attention here. You already have a sub 4 calculated here. Just substitute that, and you can find all of these even indices in terms of a sub 0. So basically, you have the following. A sub n as the even indices is equal to negative 1 to power k divided by 2k factorial a sub 0. So we found a recursive relation for even indices. Now, what about odd indices? For the odd indices, we're going to plug in other values. So far, we saw that the relationship that we have is n plus 2, n plus 1, a sub n plus 2, plus a sub 0 equal to 0, or a n plus 2 is equal to negative a sub 0 divided by n plus 2 times n plus 1. So if I plug in 1 for my n, I get a sub 3, which is negative a sub 1 divided by 2 times 3. Let me fix this one. Just a sub n. Very good. So this is our a sub 3, which can be written as negative a sub 1 divided by 3 factorial. What if I plug in 3 here? If I plug in 3, a sub 5 becomes negative a sub 3 divided by 5 times 4, which is a1 over 5 factorial. What if I plug in 5 here? So as you can see, I'm working with odd indices. A sub 7 is negative a sub 5 divided by 7 times 6, or since you already calculated a5, you can just replace that and write down all of these terms in terms of a sub 1. What is the pattern here? The pattern that you're observing is for odd indices, a sub 2k plus 1, you have negative 1 to power k divided by 2k plus 1 factorial times a sub 1. So now let us take these and write down the solution for this differential equation. The summation of n plus 2 times n plus 1, a n plus 2 plus a n x to the n is equal to 0. So we found a sub n to be a sub 2k for even indices as negative 1 to power k divided by 2k factorial multiples of a sub 0, and an for odd indices to be negative 1 to power k divided by 2k plus 1 factorial, and they are multiples of a1. So y can be written as a sub 0 plus a sub 1x minus a sub 2, which is a sub 0 divided by 2 factorial times x squared, plus a sub 3, which is negative a sub 1 divided by 3 factorial times x to the third, and so on, plus the rest of the terms, and eventually we can see that it is the combination of negative 1 to power n a sub 0 divided by 2n factorial and even powers of x plus negative 1 to power n a sub 1 divided by 2n plus 1 factorial times the odd powers of x. So basically, if you factor out a sub 0 from these terms, you can combine them as a sub 0 times 1 minus x squared divided by 2 factorial plus x to the 4 divided by 4 factorial plus the rest of the terms. And for the rest of them, you can factor out a sub 1. And as you can see, here you have a sub 1x negative a1 divided by 3 factorial x cubed and so on. So if you just factor out a sub 1, you can write down the second power series as a sub 1 times x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial and so on. So we found the power series solution for this differential equation, as can also write this in more compact form. This in terms can be written as a sub 0 times the summation of negative 1 to power n divided by 2n factorial x to power 2n. And the second one, the second power series, can be written as a sub 1 times the summation of negative 1 to power n divided by 2n plus 1 factorial x to power 2n plus 1. So we found two power series solutions. The first power series solution and the second power series solution for this differential equation, as you can see, is written just right here.